Hello everyone, welcome to the next lab of ECE573 Advanced Embedded Logic Design. In this lab, we are going to discuss how to implement fast Fourier transform on the using the SDSoC on the Zynq SoC. As we all know, fast Fourier transform is an efficient way of implementing the discrete Fourier transform on the software as well as the hardware. The fast Fourier transform reduces the number of multiplication inside the discrete Fourier transform. The fast Fourier transform has a wide range of application from the audio signal processing, image signal processing, as well as wireless communication. The FFT not only helps to reduce the number of multipliers, but the parallel computation inside the FFT can be exploited by efficiently implementing it on the FPGA or the ASIC. So, to the best of my knowledge, the fast Fourier transform is one such accelerator design developed to speed up the computation of the fast Fourier transform. The size of the fast Fourier transform in real applications can be very high. For example, in case of the 5G wireless physical layer, the size of the fast Fourier transform can go up to 4096 or even higher. So in the fast Fourier transform, your input is G, which is a vector. You multiply G with the matrix S, which is a matrix consists of the complex values, and you get the output, which is the capital G, which is a complex output. Now this S size, it's a square matrix, and the size of it depends upon the size of the FFT. So if you are doing the 2-point FFT, you get the 2 cross 2. If you are doing 4-point FFT, it is a 4 cross 4 matrix. This is the input vector. It can be 2 cross 1 or it can be 4 cross 4 or so on. And the output size is same as the input size. For example, in case of the 2-point FFT, your S consists of these 4 elements where WE is equal to e raised to minus j2 pi. Okay. So when you say W 0, 0 or 2, sometimes it is also represented as a W02. It is nothing but the e raised to minus j2 pi 0.0 divided by 2. So it is nothing but the 1. And when you have the W 2, it is nothing but the e raised to minus j2 pi 1 comma 1 divided by 2. So e raised to minus j. You have pi, and this is nothing but the minus 1. So you can see that this matrix is nothing but the 1, 1, 1, minus 1. And when you multiply the G, you get the G of 0 is equal to G of 0 plus G of 1. And this is nothing but the G of 0 minus G of 1. So you can see that using this fast Fourier transform, you don't need any multiplication. You can do this computation using the adder and subtractor. So here this structure is called as a butterfly structure. This is the butterfly structure of size 2, because the input size is 2 and output is 2, and you have only one weight, which is the W02. And how it is implemented, you take the second input, you multiply with the weight W02, and then you add it to your first input, and then you subtract it from the first input. So G0 plus G1, because this guy is 1, and G0 minus G1. So for two size butterfly or 2-point butterfly, or it is also called the 2-point FFT, you have the number of weights are 2 by 1, that is 1, that is the W02. Okay, so now we can go from the 2-point FFT to the 4-point FFT. So in case of the 4-point FFT, you have the S, which is the 4 cross 4, you have the G, which is the 4 cross 1, and you get the capital G, which is the 4 cross 1. And what are the elements of this S? Again, you can compute it in the same one. You will get W00, instead of 2, it will be 4. W014, W024, W034, then W102, W11, sorry, W44, W124, W134, and so on. So you can create a 4 cross 4 matrix. So then by exploiting the properties of this W, you will see that many W values are same. You can minimize this equation like this. So where you can see that there is some structure which you can exploit. So you can see that you are getting G0 plus G2 and G0 minus G2. Similarly, G1 plus G3 and G1 minus G3. And then you are multiplied by this factor e raised to minus j 2 pi, 0 by 4, 1 by 4, 2 by 4, and 3 by 4. And then if you notice clearly, this guy and these guys are similar except the minus sign, and this one and this one is similar except the minus sign. So you can simplify it further. And if you see here, this is nothing but the 2-point FFT which we have discussed in the beginning, and this is the same as the 2-point FFT. So you are doing the 2-point FFT. So this is nothing but like this, and then you can see that here this is the 4-point FFT. So this is in the stage 2. Once you get stage 1, you do the stage 2, you multiply with this value. So since both the values are same, what you do, you multiply by W04, W14, okay, and then you get the you do the addition as well as you do the subtraction. So this addition corresponds to here, and this subtraction corresponds to here, okay. And W04 is nothing but the e raised to minus j2 pi 0 by 4. W14 is nothing but the e raised to minus j2 pi 1 by 4. So in this case, the 4-point FFT, okay, 4-point FFT can be implemented using the 2 stages. In stage 1, you have the if you see the stage 1, you have the 2-point FFT, and in the stage 2, you have the 4-point FFT. Okay, so it is you can say that it's a butterfly structure. It's a complete 4-point FFT. Okay, so 4-point FFT can be implemented using the butterfly structure of the two. In the stage 1, you have the 2 butterflies. In the stage 2, you have the 1 butterfly of size 4. Okay, where you have the 4 in. So on the general case, for n-point FFT, you need a 2 n by 2 point FFT followed by the butterfly stage of the n size. So you have the n by 2 FFT, n by 2 FFT, and the butterfly stage, additional stage of the size n. So if you take the one thing, you need to make sure that the inputs are given in a proper order so that you get the output in the proper order. So in case of the 8-point FFT, you can see that the input needs to be given in the proper order. So if it is the 8-point FFT, you have the 3 stages, 2 to the power 3 stages, stage 1, stage 2, stage 3. In the stage 1, you will have the butterflies of size 2, and you will see that in the stage 2, you will have the butterflies of size 4. In the stage 3, you will have the butterflies of the size 3. So in case of the 8-stage FFT, you will have the 4 butterflies of size 2, then the 2 butterflies of size 2 and 1 butterfly of size 8, 2 butterfly of the size 4, and then 1 butterfly of the size 8. So you can see that you have the 4 butterflies of size 2, then you can see that you have 2 butterflies of size 4 and 1 butterfly of size 8. And what are the weights? You can see W08, W18, W28, W38. So for 8-point FFT, you need 8 by 2, that is 4 weights, and you can see that this weight is being used here, and this weight, W2 weight, is being used here. So you can see that the same weight, you need to store 4 weights, and this can be reused. So this part is clear. Only thing is how to do the bit reverse, and there is a very small simple logic is there. For example, if you take the 8-point FFT, your input can be 0 to 7. So what you need to do, you need to just do the bit reverse operation. So if it is a 001, you do the 100, you get the corresponding index. So you can see that you are getting the corresponding index. So bit reverse is just by reversing the index, you get the corresponding bit. So whenever you implement the FFT inside the Zynq, inside the hardware, you need to do the first bit reverse operation. Then you need to find out how many stages are there in the FFT. Then the first stage will be always a two input butterflies. You will have multiple two input butterflies, and in all the butterflies, the weights there will be only one weight. Okay. In the second stage, you will have the multiple four input butterflies, and you will have the two different weight. And in the third stage, you have the multiple eight input butterfly, and you will have four different weight. Then in the stage 4, you will have the multiple 16 input butterfly, and you will have 8 stage, and so on. So this is how the structure is looks like. Now we will see how to implement it on the SoC using the SDSoC. So in this code, we have implemented the three files: main.cpp, then FFT.h, and FFT software.h. And then you need to implement the corresponding hardware implementation. Okay, so in the main .cpp, we are following the same process. We have the define the inputs and output. For example, we have the imaginary input and the real input. So we have the two inputs. Then the output from the software are real and imaginary, and output from the hardware are real and imaginary. The rest of the code is same as what we have done in the previous lab. Then we are doing the FFT check. Okay, in the FFT check function, again, what we are doing, we are going to initialize the input. Then we are calling the software function. Then we are calling the hardware. So here you will call the hardware function. Since I have not implemented the hardware function, in my case, I'm calling the software function 2 times. And then you will check the result output of the software as well as the hardware. Now, what we are going to do, how to do the initialization array. So in case of the init array, you can see that for the input which we have provided to you, output.gold.dat file, the inputs are like this, where real part is same as the for loop index, and the imaginary part is the 0. So for this input, you will get the output which is there in the output.gold.dat file. So make sure you initialize this array carefully. If you want to check with the other input, make sure you have the corresponding dat file with you. Then the FFT size is 1024. In our case, you can change it for any other values. Then once you do this initialization array, then you need to do the call the function, which will check it later, and then the result check. Now in the result check function, instead of comparing the value an element by element, it is very difficult to match the element by element values in case of the most of the signal processing algorithm like FFT, because in the MATLAB or Python, you implement this as a double precision floating point, which is using the 64-bit. But here in the hardware, you will have the fixed point implementation, or the double or the float implementation, which is the 32-bit floating point. So instead of checking the element wise exact matching, we check the root mean square error. So what we do, we take the element wise value from the golden reference. We first find out the difference between the real part and the imaginary part from the golden reference for the software part as well as the hardware part. Then we do the square of that difference, root mean square error. So what we did, we first find out the error, then we took the square of that error. Okay, once we took the square of the error, then this is the same for the hardware as well as software. Then we did the mean, we divided by the FFT size, and we'll take the root value, that is the square root value. And then we plotted those corresponding error values. And if the error is greater than 1, it is up to you what threshold you are okay with. I say that it is failure. If the error is less than 1, then for me it is pass. Okay, so this is the one way you can check the your output with the golden reference from the MATLAB in terms of the root mean square error. So there are different types of errors are there. You can choose any one as per your application. So this completes the discussion on the main.cpp. Next is the FFT.h. In the FFT.h, in the conventional way, you include all the .h file. You define the FFT size, then the number of stages, that is 2 to the power 10 is equal to 1024. Then you have the definition of the function for the hardware as well as the software. And what you do is that you predefine these weights. The weights of the FFT matrix is the complex weight. So you define the real as well as the imaginary weight. So for n-point FFT, the size of this vector is n by 2. So it is for 1024, it is 512. And for 4-point FFT, you will have two weights, that is W04 and W14. Then for the 8-point FFT, you will have the four weights, W08, W18, W28, and W38. Similarly, for 512-point FFT, you have W0512, W1512. Sorry, for 1024, you will have W051, 1024, W1024 up to W511, 1024. These are the weights you need to add. Okay, so this is the .h file, and the last one is the software implementation. Okay, so now the software implementation, you have the two important things you need to do. You need to first do the bit reverse operation, and after you do the bit reverse operation, you need to implement the actual FFT, which consists of the multiple stages. Okay, so if you go back to the your slides where we discuss about the FFT, so as you can see that you have the bit reverse one, and then you have the for 1024-point FFT, you will have the stage 10. So in case of the 8-point FFT, you will have the total 8. In 8-point FFT, you will have the 3 stages. And in each stage, okay, first stage you will have the butterfly of size 2. Second stage, we will have the butterfly of size 4. In the third stage, you will have the butterfly of the size 8, and so on. So your butterfly size, it depends upon your 2 to the power stage. Okay, that is the stage index. Then in the butterfly of size 2, you will have only one filter weight, and all the filter you will have only one butterfly weight, and all the weights in the stage 1 will be same. So that means you need only one butterfly weight in the stage 1. In the stage 2, you will have two different butterfly weights. In the stage 3, you will have four different butterfly weights. Okay, so the number of butterfly weights in the stage 1 is 1, in the stage 2 is 2, in the stage 3 is 4, in the stage 4 is 8, and so on. So the number of butterfly operation in parallel, in stage 1 it will be, in case of the 8-point FFT, it is 4, so it is n by 2. Okay, in case of the 102.4 FFT, it will be 512. This 512. In case of the 16-point FFT, there will be 8 input butterfly in the stage 1. In the stage 2, they will reduce by 2, and so on. So you will have 4 to 1, or in case of the 16-point FFT, you will have 8, 4, 2, 1, and so on. Okay, so the same logic is written in the software implementation. So if you go to the software implementation, you can see that the first stage is doing the bit reverse operation. So software implementation of the bit reverse is very simple. I just write the small function where I'll take the first bit of the index, and I'll shift it to the left by 9, the second by 7, 5, 3, 1, and then I'll do the right shift. So the logic behind this is very simple. So suppose that my input, now I'm doing the 1024 pointing FFT, so my input index can be a 10-bit index. So if I take it like this, 1, 2, 3, 4, 5, and 1. So this is my input index, and as the bit reverse logic, my output is the like this. So how I come from here to here. So what I do, I take the first bit, I shift it to the 9 location, I get the 1 here. I take this one, I shift it by 7, I get this. I take this one, I shift by 5, I get this one. I take this one, I shift it by 3, I get this one. Then I take this one, I shift by so 7, 5, so 9. So this is 9, then this is 7, this is 5, then this is 3, and then this is 1. So I shifted by 1, I'll get this one. So this is the left shift. Then I'll again shift this is by 1, but I'll shift it to the right hand side. I'll get this one. Then I'll shift it by 3, then shift it by 5, 7, and 9, and I'll get the 1, something like this. So the same logic is written in the code. So if you look at the code, what we do, uh, so we have shifted by 9, 7, 5, 3, 1, and then to the right hand side shift by 1, 3, 5, 7, 9. And what we do, we extract the first bit by multiplying by 1, then by 2. You can see 2 means 1 0, so we extract the second bit. 4 means 1 0 0, we extract the third bit. 8 means 1 0 0, we extract the fourth bit. 1 0 means in the hex is 1 0 means in the binary it is 16, so we extract the fifth bit and so on. Okay, so this is how we do the bit reverse. Then you can see that I have the first for loop. I have the total 3 for loop. One is the stage, second is the butterfly, and third is the size of the butterfly. So you can see that in the stage 1 to the 10 stages. Then in each stage, I find out the what is the size of the FFT I'm performing. So you can see that I'm in case of the stage 1, I'm performing the 2-point FFT. In case of the stage 2, I'm performing the 4-point FFT, and so on. So then find out the butterfly width. So you can see that once I find out the 2-point FFT, this indicate the number of weights in the butterfly. So you can see there is only one weight in the butterfly. In case of the 4-point FFT, I'll have the 2 weights in the butterfly. So this is nothing but the FFT size divided by 2. Then I go to the butterfly stage. Here this loop will run based upon the how many different butterfly weights are there in the corresponding stage. So you can see that in the stage 1 there is only one butterfly weight, so this will run for only one time. In the stage 2 there are 2 butterfly weights. In the stage 3 there are 4 butterfly weight. In the stage 4 you will have the 16 butterfly, so you will have the 8 butterfly weight. So this loop will run one for every butterfly weight. So you calculate those butterfly weight from the matrix array which is stored in the .h file, and this loop will run for the number of butterflies. So you can see that in the stage 1 the number of butterflies are n by 2, then FFT size by 2, so 1024 by 2, you will run it for this many times. Then in the second stage, this will be FFT size by 4, so you will run for this many number of times. And then at the end, you are doing the complex multiplication. So what you do, so we'll go back to the slide. So here what we are doing, we are first extracting, we are taking the G of 1. Then we are multiplying by W corresponding weights, W02. Then we are adding it to the G of 0, and then we are subtracting it from the G of 0. Okay, and then we get the corresponding weight. So the same thing, only in here in case of the complex one, you have the, for one complex multiplier, you have the 4 multiplication. So you can see that you are doing the this multiplication to find out the G of 1 into W02. Then you are doing the subtraction. So you are finding out the G of capital G of 1, and then here you are finding out the capital G of 0. And the same thing will be repeated for the number of two butterflies you have in your code. Okay, so this is how the FFT is implemented. So now your task is to implement this in the software, verify the code, and then implement efficiently on the hardware.